My name is Julieta Diaz and I'm a data scientist at TIBCO. Welcome to this Team Studio enablement video. In this video, I will cover how to use Team Studio to solve a clustering task. We are going to use the Kmeans and SelfOrganizing Maps operators. We are starting from the Word Files tab in a workspace I have previously created, and we will click on the clustering workflow to get to the workflow canvas you can see here. Clustering is the process of dividing the entire data into groups, also known as clusters, based on the patterns in the data. So let's say we want to do some clustering on the famous iris dataset. This dataset includes 3 iris species with 500 samples each, and it is composed of 5 columns. 4 columns of measures on the sepal and pearl, and the column containing the labels, setosa, versicolor, and virginica. So in this case, we are going to suppose that we only have the independent variable and not the target variable, which is the species, the feature with the labels. Hence, this is an unsupervised learning problem, and we will implement 2 different models to solve it. You can find all the model operators that are available to you by selecting Model from the Operator drop-down, and we can see the different options that we have. In this case, I'm going to drag in the Kmeans clustering and the SOM clustering operators, both of them for clustering tasks. So if we connect our training set to the models, we then have to configure them. Let's start with the Kmeans. This method is one of the simplest and most popular unsupervised machine learning algorithms. The Kmeans clustering techniques tries to minimize the distance of the points in a cluster with their centroid. The first thing we need to define is the predictor variables. We can decide if we want to use all the available columns or not. When we set it to yes, the operator uses all the available columns as predictors and ignores the continuous predictors parameter. Otherwise, we must select at least one of the continuous predictors. For our purposes, I'm just going to use all the available columns. We can also select the distance measure for training the model. The options available are Euclidean and Gaussian. The next parameter is the number of clusters. The default value is 2, but I will change this and add other options. Let's say 3, 4, 5, and 6. To determine the optimal number of clusters, this operator uses the silhouette metric, a measure to compare the similarity of observation to its assigned cluster to other clusters. We can also define the method for specifying the initialization cluster points. It can be either random or the Kmeans++. This last option selects initial cluster centroids using sampling based on an empirical probability distribution of the point's contribution to the overall inertia. This technique speeds up convergence. There are more parameters we can modify, like specifying if we want to normalize the numerical features, how many iterations we would like to perform for one run of the Kmeans algorithm, the convergence tolerance, and the random seed. If you want to look at the documentation to better understand the parameters, you can just click on the question mark. Let's have a look at the SOM clustering operator now. This operator implements the self-organizing maps algorithm that generates the clusters spatially aligned according to their similarity. It is a type of artificial neural network that produces clusters spatially aligned on a grid, where clusters close to each other are more similar. Self-organizing maps differ from other artificial neural networks as they apply competitive learning as opposed to error-correcting learning, such as backpropagation with gradient descent, and in the sense that they use a neighborhood to preserve the topological properties of the input space. As we can see, the parameters of this operator are similar to the parameters of the K-means clusterings. We can configure the columns that we will use as predictors, the number of clusters, the maximum number of iterations, the tolerance, etc. The parameter number of cluster specifies the grid dimensions, which controls the number of clusters to create during the self-organizing maps. For example, the default value is 2, which is equal to 4 clusters grid. Once we have created and configured the models in TeamStudio, the predictor operator needs to be connected to the models if we want to perform the clustering against our dataset. So here, the input to the predictor is the dataset and then the different models. Once the analytical flow has finished, we can check the information that the clustering operator provides. So, for example, in the K-means clustering, we have a table showing the training cost per number of clusters. This is the sum of the specified distances to the nearest centroid for all points in the training set. And we also get the silhouette value. Generally, high silhouette values are preferred. In this case, the optimal number of clusters is 3, which coincides with the number of species of the iris dataset. We have similar output of the SOM clustering operator. If you look at the output of the predictor operator, we can notice that with each of the models, there are 2 columns that appear, which are called pred and dist. The pred column specifies the cluster that the observation belongs to, and the dist column is the distance between the cluster centroid and the observation. Km refers to K-means clustering, and SOM refers to self-organized maps clustering, as you can see in the summary section. Thank you for watching.